Hey, welcome back for lesson 10. This lesson is called Rational Numbers and Equivalent Fractions. Let's go ahead and jump into it. Okay, objective 1 is to define rational numbers. To help us do that, we're going to use this nice little chart here. Okay, rational numbers are just any number that you could include on a number line. Okay, so if I draw a number line here, say I put 0 and 1 and 2, and we could go 3, 4, 5 and all of those. I could also have the negatives. Okay, so rational numbers are positives, they're negatives, they are 0. Okay, but then we can also include fractions and decimals. Okay, so fractions and decimals go in the rational numbers. So on my number line, I could sure put in fractions and decimals. I could put 1/2 right here. I could put negative 0.5 right here. Okay, and I could include more of them if I wanted to on that number line. So rational numbers are positives and negatives and fractions and decimals and 0. Okay, and they could be positive fractions or negative fractions, and they could be positive decimals and negative decimals. Alright, remember integers, our friends integers, were those positives and negatives, okay, but no fractions and no decimals. So integers were the numbers that look like this, and then their opposites. Okay, so integers are no fractions and no decimals. Okay, so that's integers. Then we got whole numbers. Remember, the whole numbers were the numbers that we would count by plus 0. Okay, so again, it's 0, and then if I told you to start counting, and actually we shouldn't put the arrow on the end here on this number line because it doesn't go back any farther. 0 is where it starts. And then I could go 1, 2, 3, 4, so on. Okay, so whole numbers are no negatives, no fractions, and no decimals. Okay, so again, rational numbers are any number you can put on the number line. Positives, negatives, zeros, fractions, decimals. Okay, integers are no fractions and no decimals, but any other number. And then whole numbers are no negatives, no fractions, and no decimals, but any other number. Okay, let's move on to the next slide. And actually, there's one last thing I wanted to mention before we go on to the next slide that I almost forgot, and I want to come back and tell you, is that rational numbers include integers and they include whole numbers. Okay, so whole numbers are also in the integers group, and they're also in the rational numbers group. Integers, okay, are those positives and negatives. They are included in rational numbers as well. Okay, so rational numbers include all of these types of numbers in here. All right, now let's go on to the next slide. Okay, so our first example is to describe each of these numbers that are written down here as a whole number, an integer, or a rational number. Okay, this part's key, right? Every term that applies. Then sketch a number line and graph each number. Okay, well, let's look at -3 first. Is -3 a whole number? Okay, well remember, whole numbers cannot be negative, so it's not a whole number. But we know that -3 is an integer, and we know that -3 is a rational number. If it's an integer, it has to be rational. Okay, let's look at the number 2. Well, number 2 goes in the whole number category, so it is also an integer, and it is also rational. Okay, 3/4. 3/4 is not a whole number because whole numbers can't be fractions. It's not an integer because integers can't be fractions, but it is a rational number. Okay? Then it says to sketch a number line and graph each number. So we're going to make us a number line. Okay? And our number line has to go from at least -3 to +2 because that's our lowest and our highest numbers. So I'm going to put -3, -2, -1, 0, 1, and 2 in here. Alright, then I'm just going to graph these. Well, here's -3. Here's +2. And then we've got to put on 3/4. Okay, 3/4 is between 0 and 1, but it's closer to 1, so I'm going to put it right here. Okay, now, when you graph fractions, I want you to go ahead and write the number you're representing above it. Or actually, let's go below it. Okay, so this right here is supposed to be 3/4. Alright, so when your dot is right on the line, like this one, okay, we know that's -3. This one we know is -2. This one could be another fraction, okay, we're just kind of guessing where it is, so we need to put what number it represents down here. Alright, let's go on to another example. Okay, we're here with objective 2 now. Objective 2 is to reduce and compare fractions. First we got to know a couple terms. The first term to know is equivalent fractions. Equivalent fractions are fractions that are the exact same size. Okay, so if I draw some pizzas here, I split them up into equal pieces, or as close as I can make them to equal pieces. Alright, so if I was to shade in this first fraction so that it's 4/8, okay, so there's 4/8 right here, and I shade in this pizza so it's 3/6. And I shade in this pizza so that's 2/4. And this pizza so that's 1/2. Okay? We should be able to look at each one of these pizzas and realize that that is all the same amount of pizza. Okay? So 4/8 is the same as half a pizza. 3/6 is the same as half a pizza. 2/4 is the same as half a pizza. Alright? So, again, equivalent fractions are fractions that are the exact same size. Well, I could divide this number, okay, 4/8, I could divide the top and the bottom by 4. And 4 divided by 4 would give me 1. And 8 divided by 4 would give me 2. So it's 1/2. I could divide this top and bottom by 3 and simplify it. 3 divided by 3 gives me 1. 6 divided by 3 gives me 2. Same thing if I reduce it. And I could reduce this one by dividing the top and the bottom by 2. Well, 2 divided by 2 is 1. 4 divided by 2 is 2. So all of these fractions, 4/8, 3/6, 2/4, and 1/2, are equivalent to each other because they're all the same size. Alright? Another definition you need to know is reduced. Okay? A fraction is reduced if it is all the way simplified. Alright? So 1/2 is a reduced fraction because I can't simplify it anymore. 2/3 would be a reduced fraction because I can't simplify it anymore. Alright, so that's what reduced means. It's all the way simplified. If I look up here, 4/8 is not reduced because I simplify it to 1/2. Same thing with 3/6 and 2/4. They are not reduced. Now let's look at an example. Example 2 says they want you to use prime factorization to reduce 72 over 108. Okay, so prime factorization is where we use the factor trees or the downward division to break down the number into its prime factors. So I'm going to do one of each method here. With 72, I'm going to use factor trees, and with 108, I'm going to use downward division. Okay, you can use either method. It doesn't matter to me. Okay, I'm just picking these two so I can show you one of each. So 72, that breaks down many ways, but the one that most of you will recognize probably is 8 times 9. Okay, 8 is not prime, so we got to continue to break it down. 8 is 2 times 4. Well, 2 is prime, but 4 is not, so we can continue to break down 4. It's 2 times 2. Now over on this side of the tree, I'm all the way done because I've got prime numbers I can't break down anymore. Well, 9 is not prime, so I've got to break it down. And it breaks down into 3 times 3. And both of those numbers are prime. Okay? So, to reduce this fraction, 72 over 108, I'm going to list out all of the prime factors of 72 on top first. So I've got 2 times 2 times 2 times 3 times 3. And we should remember what form this is called. I'm writing in expanded form. Okay? So make sure you write out in expanded form. Well, let's do 108 by downward division or division of primes. Okay, again, first number you always want to check, first prime number is 2. So see how many times we can get 2 to go into this. 2 goes into 108. I know that because 108 is even, and 108 divided by 2 is 54. And I divide again. 2 goes into 54 because it's even. And 54 divided by 2 is 27. If you didn't know that, do it up here. 54 divided by 2. 2 goes into 5 twice. 2 times 2 is 4. Subtract and get 14. 2 goes into 14 7 times. Alright? 2 will not go into 27 because 27 is not even. So the next one I need to try is 3. And 3 goes into 27. Okay, and it goes in 9 times. Then, I know that 3 goes into 9. 3 times. Alright, now my number down here at the bottom is prime, so I'm done. I'm going to make my awesome little booty. Pretend like it's an Iowa Hawkeye booty. And I'm going to write out those prime factors over here on the bottom for 108. Okay, so 108 in prime factorization is 2 times 2 times 3 times 3 times 3. Now, to reduce this, what we're going to do is I'm going to cross out any numbers that I see on the top and the bottom. Okay, so what the top and the bottom have in common until I can't do that anymore. Well, get my red pen here. Top and the bottom both have a pair of 2's. Okay, and they both have another pair of 2's. Then they both have a pair of 3's, and then they have another pair of 3's. Okay? So now what we're going to do is I got no more matching pairs on top and bottom. So what I'm going to do is I'm going to multiply together any numbers on the top, and that's going to give me my reduced top number. Okay? Well, on the top, I only have one number. If I had 2 numbers, I would take those and multiply those together, but I don't. I only have 1, so I'm just going to put 2 down here. On the bottom, same thing. If I had more than one number down here that wasn't crossed out, I would multiply them all together, but I only have 1. So I just put my 3 on the bottom, and here's my reduced fraction. Okay? That fraction is all the way simplified. And that method works every single time. So when they tell you to use prime factorization to reduce it, this is the method I'm looking for. Show me the factor trees or downward division. Show me expanded form of the numerator and expanded form of the denominator. And then cross out what they have in common and multiply what's left over. Or just write down what's left over if it's only one thing. Okay, let's go on to another example.